Good morning, everyone. My name is Atalla, and I'm going to tell you today how we can use ultrasonic vibrations to control friction in endovascular applications. So, in typical catheterization procedures, interventions inserts catheters into blood vessels and then navigated through vasculature until they reach the region of interest. During this navigation phase, the relative sliding between catheters and blood vessels introduces complications such as bleeding, perforation, and degradation of the internal wall of the artery, which can cause post-operative thrombus formation. So, in that sense, having low friction is desirable to reduce these complications and allow for seamless navigation of the catheter. However, once we start executing the actual task, like installing a stent or removing a blood clot, contact between catheter and blood vessel forms anchor points which are necessary to maintain stability for the catheter. So in that sense, having high friction is desirable to maintain the catheter stability and allow for precise task performance. So the question is, how can we manage the different friction requirements for each phase? Looking at the current practices, one of them is by applying lubricants directly to the catheter, which is restricted to relatively short distances and is enabled to switch between high and low friction state depending on the phase. And another alternative is using self-lubricating catheters like hydrophilic ones, for example. However, this also lacks the ability to switch between high and low friction states. So the limitations of these existing practices suggest that the need for an active friction modulation strategy. And the question now, how can we create an instrument or a catheter whose friction properties are actively controlled such that we have a low friction state while navigating and high friction state while executing? So one technology that can potentially answer this question is ultrasonic lubrication. But let's take a step back. What is actually ultrasonic lubrication? So when you have two objects in close contact to each other and we start vibrating one of them at ultrasonic frequency in transverse direction, it was found that a pressurized squeeze film of fluid from the surrounding medium is created, which separates the two surfaces slightly away from each other, resulting in reduced friction when they start sliding with respect to each other. This phenomenon is called squeeze film levitation, and it has been exploited in different applications, including surface haptics, touch screens, and squeeze film bearings. One thing that you realize when you look at these applications quickly is that they are all working in air-dry environments, which is far from the actual environments of a catheter. So one of the very early questions that we asked is, okay, what if we take this vibratory system and we place it into a liquid environment with viscoelastic interface? Will it still work or not? And the answer we got is that it actually works, and we derive the law that basically predicts the separation between the two surfaces given the vibration amplitude, frequency, and the fluid properties. So now that we know that this technology can work in the relevant environment, the question now of how can we translate this into an actual design? So we looked into the design requirements for application. We need a tubular design that has a lumen, and it has to be potential to be downsized. And the technology requires that the vibration amplitude reaches higher than 2 microns of amplitude and to vibrate at resonant ultrasonic frequency. So we came up with a discrete friction control module design where the shaft of the catheter featured friction control modules, discrete friction control modules. These modules can vibrate through a piezoelectric actuated modules and can vibrate with this flexural vibration mode. And to validate this design, so we implemented this design at different scales. The biggest one was 15 millimeter, the smallest one was 4 millimeter. We used laser Doppler vibrometry to scan the surface of the vibrating elements, and we validated. Okay, so you have to believe me in that. It vibrates according to its desired design. And it achieved a maximum vibration of 3.9 microns, and it resonates at 22 kilohertz. So now it's time to validate this design in friction experiments. So we took this friction control modules, and we started doing friction experiments against ex vivo soft tissue that represents healthy arteries, and also rigid tissue that represents rigid material that represents calcified arteries. So the experimental procedure starts by lubricating the surface, pushing the friction control modules against the surface, sliding, measuring forces, and repeating this sequence many times. So looking at the results, we see that our friction measurements show that our system is capable of reducing friction. So if you look at the coefficient friction, you see that it drops immediately once we start applying vibrations. And if we repeat this sequence again on different samples and on different paths in the same sample, we can observe that friction reduction can be achieved across all samples and across all paths, validating that the design is feasible. And yeah, we were able to achieve 38% friction reduction across all samples on average. And if we look at the relation between the coefficient friction after we activate vibration versus the coefficient friction before we activate vibration, this line represents the no friction modulation. Once we stop vibrating, we get into this friction modulation zone. And we found a linear correlation between the coefficient friction off case versus on case, which basically tells us that the range between the friction modulation in off and on case depends on where do we start in the on and the off case. So basically we need to start from a sticky design and then vibrate to get bigger range of friction reduction. We also looked into the thermal safety, so we conducted thermal camera experiments where we activated these vibratory elements and we started sliding against tissue, and then we started activating these vibrations and we measured the temperature rise that happens in tissue. And what we found that we got a temperature rise on average 6 degrees. It's worth 6 degrees Celsius. This is important. It's worth noting that this temperature rise was very local to the contact area, and of course it did not take into account that blood vessels have a blood stream going, which can reduce this further. One thing also we started looking at to demonstrate the potential of this technology is whether this technology can be used to reduce or eliminate buckling in catheters. So usually when you insert catheter into a lumen and starts to face some form of resistance, it buckles, and this buckling can result in excessive force exertion on tissue, which can be dangerous. So what we did, we started looking at if we integrate one friction control module at the tip and we start inserting this catheter into a lumen, you can see that in the off case, without any vibrations, the catheter buckles as we expected. However, when we activate vibrations, it maintains its configuration, confirming that we can eliminate buckling and we can have buckling-free insertion process. So now interventionists can enjoy slippery, buckling-free catheter navigation. Thank you.